Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away.
46, 56 degrees.
Hi, everybody. I love this theater. I love this film. I'm so thrilled to be here. We have a lot to do, so let's get started. Let's set the stage. So to set the mood, A Serious Man starts with an eerie tale set in a 19th century Eastern European Jewish village, spoken entirely in Yiddish. It's a mixture of mostly German and Hebrew. But the film mostly takes place in a predominantly Jewish Minnesota suburb in 1967. The protagonist is Larry Gopnik, a physics professor whose luck takes a comically excessive turn for the worse. There's Larry. Here's Larry fiddling with an antenna on the roof. This is an extraordinary film. The late, great film critic Roger Ebert gave it 4 stars. Don't worry if you haven't seen the film before. This talk will be self-contained, and I'll be careful to avoid giving away any spoilers. First, a glossary of relevant Hebrew and Yiddish terms in the film. Ivrit, Hebrew, literally Hebrew, the language the kids in the film are supposed to speak during their religious schooling. Here they are looking very excited. Many American Jewish children attend afternoon or weekend religious school until they reach the age of 13, when they have a bar or bat mitzvah ceremony to celebrate becoming adults in the eyes of Judaism. And some continue, some don't. Torah, Hebrew, from the Hebrew for instruct, the 5 books of Moses. They tell the story of, the creation of the universe, the beginning of the Abrahamic faiths, the time of the Israelites in Egypt, their escape to the desert led by Moses, and their arrival to the Promised Land, along with a list of many religious laws. And it's contained in a sacred scroll in synagogues. Those are places of Jewish worship. Here's a Torah in its wrapped up, and here's a Torah being read during a religious service. And the Torah is read or chanted out loud in Hebrew during religious services. Hashem, Hebrew, literally the name. This is used to refer to God outside of prayers as a sign of respect, and you'll see this used a lot in the film. Goy, Hebrew/Yiddish. Its plural is goys or goyim. In biblical Hebrew, usually translated as nation. It began to refer to non-Jews in the 1st or 2nd century AD. Shul, Yiddish, from the German for school, a synagogue. Dybbuk, Yiddish, from the Hebrew for the act of sticking, a human body possessed by the evil spirit of a dead person. You'll see why this image is relevant soon. Tzaddik, Hebrew, from the Hebrew root word tzedek for justice or righteousness. A tzaddik is an extraordinarily righteous person. The Zohar and the Kabbalah, Hebrew. The Zohar, literally splendor or radiance, is a collection of books, likely written in the 13th century AD, that are the core texts of the Kabbalah, reception, or Jewish mysticism. You'll see why this is relevant in the film. Lamed Vavneks, combination of Hebrew and Yiddish. So Hebrew letters can be used to represent numbers. That will also feature in the film, by the way. The Hebrew letter Lamed represents the number 30, and Vav, the number 6, they add together to make 36. The Yiddish suffix nik means the word applies to a person. According to legend, the world's redemption at any time depends on the existence of 36 hidden righteous people who are so humble that they don't even know that they're special. Interestingly, the Hebrew word chai means life and is spelled chet yud. The corresponding number is chet 8 plus yud 10, 18. So 36 has another significance. It's sometimes called a double chai. Little biblical numerology there. Rashi, an acronym for Rabbi Shlomo Yitzhaki. This was an 11th century French rabbi and a widely revered interpreter of the Hebrew Bible. Here's an illustration of Rashi. The film opens with the following epigraph. Receive with simplicity everything that happens to you. Okay, let's talk about the book of Job. So the book of Job is part of the Ketuvim, the writings. This is the third and final part of the Hebrew Bible. The Torah, by the way, is the first part of the Hebrew Bible. The book of Job is thought to have been written between the 7th and 4th centuries BC. According to the story, Job is a man who lives in the land of Uz. Note, not the land of Oz. Job is wealthy, has a huge family, is extremely pious. God adores Job, but a divine prosecutor, the Hebrew is ha-Satan, and there's some debate over whether this is supposed to be Satan, or claims that Job is only pious because God has been rewarding him with such a good life. To prove otherwise, God responds by letting the divine prosecutor destroy Job's possessions, kill his family, and inflict him with a terrible rash over his entire body. It's even worse than a sebaceous cyst. This is a picture, a painting called Job on the Dunghill. This is depicting Job after all these terrible things have happened to him from 1881. The book of Job has some great lines that also happen to be highly relevant to the film. Job 14:1 says, "Man that is born of a woman is of few days and full of trouble." Yeah. Job 28:20, 21. "But whence does wisdom come? Where is the source of understanding? It is hidden from the eyes of all living, concealed from the fowl of heaven." Yeah. Job 33:14 through 17. "For God speaks once, twice, though man does not perceive it. In a dream, a night vision, when deep sleep falls on men, while they slumber on their beds. Then he opens men's understanding, and by disciplining them, leaves his signature to turn man away from an action, to suppress pride in man." I'm calling this out because, as you'll see, dreams play a very important role in the film. So in his despair, Job is visited by 3 old friends. Three people giving him advice. Well, there's kind of a 4th person, but let's just say it's 3. They bring very unhelpful advice and insist he must somehow be to blame for his misfortunes. This is a painting of Job being visited by his friends. Job demands to present his case to God. Eventually, God responds to Job, according to the story, out of a tempest. Maybe a tornado? Don't know. And expresses offense at Job's hubris. "Where were you when I laid the earth's foundation? Do you know the laws of heaven or impose its authority on earth? Have you ever commanded the day to break or assigned the dawn its place? So basically, who do you think you are, little man?" Job apologizes and recants. God relents and blesses Job with, according to the story, twice what he had before: good health, a new family even bigger and better than the last one, and great wealth. Job lives to see 4 generations of his descendants. The end. It's a painting of Job restored to prosperity. Note that Job never finds out why all these terrible things happen to him. Somehow, he learned to live with the mystery. So was a serious man actually inspired by the book of Job? Well, in an interview after the film came out, the Coens said no. Joel Coen said, "We weren't thinking this was like the book of Job. We were just making a movie. We understand the reference, but it wasn't in our minds." But it is difficult not to see the parallels. Okay, so this wasn't just a talk on theology and linguistics. Let's talk about some physics. There is so much physics in A Serious Man. Okay, first, a little something about Newton's universe. You know Isaac Newton, 17th century mathematician and physicist. According to Newton, the universe consists of the following ingredients: 3-dimensional space. This theater is a good example. Good 3-dimensional space in this theater. Filled with objects. A lot of objects here that have mass, yes, and shape and volume, with positions and velocities and accelerations, just how fast the velocities are changing, that interact with each other via forces through time. All important ingredients. Okay? So you've got this concrete world of things with places and shapes and moving and bumping into each other. It's a picture that's discernible. Newton's laws, which form the foundation of Newton's picture of the universe, are 3. 3, again, interesting, 3. First law, you've probably heard of these, right? An object at rest will remain at rest, and an object in motion will remain in motion with a fixed direction and constant speed unless acted upon by an external force. Newton's second law, force equals mass times acceleration. Maybe this is bringing back painful memories. F equals ma, F is force, m is mass, a is acceleration. I want to call your attention to the third law. Every action has an equal and opposite reaction. What that means concretely is, if an object A exerts a force on an object B, well then B exerts a force of the same strength but opposite direction back on A. This is the mathematical version of that statement. The minus sign just means opposite. As the film's protagonist, Larry Gopnik, puts it, here's Larry. Actions always have consequences. In this office, actions have consequences. In Newton's universe, at least in principle, everything is knowable, and there's a reason for everything. As Larry should know, however, we don't appear to be living in the universe of Newton's imagination. Let's talk a little bit about quantum mechanics. So quantum mechanics is over a century old at this point. It'd be hard to call it, a new theory that's replaced Newtonian physics. By the way, the quantum in quantum mechanics refers to the fact that some quantities in some situations that might seem like they should be smooth and continuous, like energies, momenta, turn out to show up only in discrete amounts. It's where quantum mechanics gets its name. But actually, this isn't the part of quantum mechanics that's going to be of most interest to us. Let's go through the standard axioms as you might read them in a textbook. There will be math. Whether we like it or not, the language for describing the universe is mathematics. As Galileo Galilei wrote in his essay, The Assayer, in 1623, by the way, it is a very angry essay. He's really, you should read it at some point. It's amazing. Anyway, there's this beautiful passage in that essay. Philosophy, by which he meant what we would call physics today. It was called natural philosophy back in his time. Philosophy is written in this great book that is constantly open there before the eyes, I say, the universe. But it cannot be understood unless one first learns to understand the language and know the characters in which it is written. It is written in the language of mathematics, and the characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand one word. Without these, one wanders vainly in a dark labyrinth. It's the Italian. It's a pretty close translation. I know, because I plugged it into Google Translate. Or, as Larry describes the situation, here's Larry, you can't really understand the physics without understanding the math. The math tells how it really works. That's the real thing. The stories I give you in class are just illustrative. They're like fables, say, to give you a picture, an imperfect model. I mean, even I don't understand the dead cat. The math is how it really works. I'll keep things as simple as I can, though. We have to start by talking about wave functions. So a physical system is described mathematically using this funny-looking symbol. It looks like Poseidon's trident, and it's encased in this weird frame, kind of like a vertical line and a weird angle bracket. It's called a wave function. More technically, it's a state vector, but we're not going to worry about the distinction. We'll call it a wave function for now. So here, this is Greek letter. This trident Greek letter is called psi, which physicists pronounce psi, as in Cy Abelman. I love this quotation. It's one of their interviews. Ethan Coen said, well, our parents were both academics, and so a lot of the people that we knew were insufferable. Okay, I got to talk about the simplest quantum mechanical system. It's called a qubit. So as an example of a quantum mechanical system, consider a qubit. This is short for a quantum binary digit. Actually, the name is itself inspired by the biblical qubit. If you've read the Bible, there's the Qubit. It's biblical, it's classical. This is the quantum qubit, you see? It's good. So a qubit is like a microscopic coin. It can be found heads up or tails down. Qubits are the basic building blocks of quantum information and quantum computing. Probably you've heard about this. Very exciting. In the real world, qubits can be constructed out of particles like photons or electrons that can spin one way or they can spin the other way. I guess this is where the discreteness of quantum mechanics comes in. They have two possible states. There are other practical implementations as well. I'm not going to be so interested in how to implement these things. Let's talk about some of their features. So we could write, this trident symbol up or the trident symbol down. These two possibilities can be expressed in terms of the following wave functions. There's the wave function labeled up and the wave function labeled down. When I put it in those brackets, I'm describing two possible wave functions. What the wave function up means in practice is that if you measure whether the qubit is up or down, you will definitely find that it is up. If instead it's the wave function down, then you'll definitely find when you measure it the qubit is down. Weirdly, the wave function can also be in a blend. We call this a quantum superposition of these two cases. The simplest kind of quantum superposition looks like this. Right? So this is a wave function psi, and it's this weird, it looks like like arithmetic, like we're adding these two things together. We're adding up to down, but they've got an x and a y in front of them. Those x and a y, those are numbers. Well, there's a guy named Max Born. He won his Nobel Prize for recognizing that if you look at those numbers, if you check whether the qubit is up or down, well, x squared tells you the probability that when you measure it, you'll find that it's up. Y squared, y times y squared tells you the probability that you'll find it down. Note, probabilities have to 100%, and that means that x squared plus y squared equals 1. If the result turns out, in fact, it was up, you measured it this weird superposed wave function, and you find up, well, then the whole wave function collapses. Now it's the wave function up. That ensures that if we measure the qubit again, we'll definitely find up as before. Makes sense. Similarly, if we had instead measured the wave function, but this time found down, then the whole wave function would collapse to down. This ensures that if we measure it, we'll find down. So let's just summarize. This was the hardest part, okay? If we start with this wave function, this funny blend of up and down with numbers x and y, and we measure whether the qubit is up or down, then with probability x squared, we'll find up, and the wave function will collapse to the up wave function. Whereas with probability y squared, we'll find down, and the wave function will collapse to the down wave function. Now, you might reasonably wonder, why is this actually strange? I mean, don't we use probabilities all the time? I mean, when we don't know the outcomes of, like, the toss of an ordinary coin, someone tosses a coin and then hides it and says, guess, heads or tails. Well, you don't know what it is. There's a probability, something that it's heads, probability that it's tails. Why is this any different? These classical kinds of probabilities are called epistemic. Epistemic refers to knowledge or belief. What makes the probabilities of quantum mechanics so different? Why aren't wave functions merely epistemic too? Here's why. I'll give you 4 reasons, and all 4 of them show up in the movie, some way or another. The first, non-commutativity or contextuality, and I'll tell you what all these mean. The second you've probably heard of. This is the uncertainty principle. The third is called interference. And the last is entanglement, and the closely connected concept of non-locality. Let's discuss each of these in turn. So the most important reason why wave functions can't be purely epistemic is that measurements of the properties of a quantum system, even when carried out as perfectly and gently as physically possible, don't always commute. Commute. Remember commute, like 5 times 4 equals 4 times 5? We say that's commuting. What do I mean when I say that measurements in quantum mechanics don't commute? Well, this behavior is called the non-commutativity or contextuality of measurements. So explain, let's go back to our qubit. Remember, it's our quantum coin. It could be up or down. Let's call A the property of being up or down. If we measure A, we could find up or we could find down. But the qubit has other properties too. One other property, which we'll call B, we could call it the left or right property. If we measure B, we could find left or we could find right. Okay, that's not so shocking, not so surprising. But here's the thing. If we measure A, the up or down property, and find some result, and then we measure B, the left or right property, and find some result, then measuring A could yield a different result from before. That is, it matters which order we carry out our sequence of measurements, even if we're as careful as physically possible. It'd be like guessing the coin, it's tails, and then guessing, oh, and it's also a quarter, and then it turns out now it's not tails anymore. Now it's heads. That's weird. So the probabilities of quantum mechanics can't just present simple ignorance of what's going on, and measurements can't merely be passively revealing pre-existing facts. This is codified, by the way, for those, keeping score, in the Coen-Brothers theorem, which was proved, interestingly, in 1967, the same year as the film takes place. Interesting. Look back at our qubit. If we measure A and find up, okay, well then we're sure to find up if we measure it again right away. We know it's up. Right? That's because whatever the wave function was originally, finding up will collapse it to the up wave function. But it turns out the up wave function is a blend or superposition of left and right. So if we next measure b, we actually have a 50-50 chance of finding left and right. Those square roots there, because remember you have to take the square to get the probability, and 0.5 is 50%. Suppose we measure it, and 50-50 left to right. Suppose we find right. Then the wave function will collapse again. Now it will become the right wave function. But it turns out the right wave function is a blend of the up and down wave functions. So if we measure A again, we might find down this time with 50% odds. So the choice over whether to measure A or whether to measure B, that's called a measurement context. Contexts are sort of like perspectives. Different contexts, like different perspectives, could lead to very different results. And no one context, like no one perspective, gives a complete picture. That's why quantum mechanics is said to be contextual. Perspectives. This leads right into a discussion of the uncertainty principle. So notice the more we know about the value of A, the up or down property, the less we know about the value of B, the left or right property, and vice versa. Indeed, if we know A exactly, then B is 50-50. It's completely unfixed. And the same the other way. This is the famous uncertainty principle. It means that as we measure the various properties of a quantum system, we don't approach perfect knowledge. Just like poor Job, we're all epistemically limited beings. Or as Larry explains, the uncertainty principle, it proves we can't ever really know what's going on. A bell sounds, the students start to leave. So it shouldn't bother you not being able to figure anything out, although you will be responsible for this on the midterm. Larry could just as easily be talking about the challenge of trying to live a good and moral life, couldn't he? Things are actually even weirder than all that. So recall this wave function. We've seen this a few times now. This is old hat now. Here's a different wave function. That's interesting. It's got a minus sign there. Remember, the Born rule tells us that you're supposed to square numbers to get the probabilities. And remember, a negative times a negative is a positive. So if you square that negative y in front, you get the same answers if you squared y. And that means the probabilities for the up or down property A are actually the same for these two wave functions. You might say, well, then what's the difference? Well, they are different wave functions. And in fact, if you measure other properties, you might find different results. But I want to call your attention to something in particular. We can blend these two wave functions together. In that case, the plus y down wave function from the first and the minus y down from the second, they cancel each other out. This phenomenon is called interference, and it's crucial for why quantum computers can calculate some things faster than ordinary computers. There is no analog of interference in the case of classical epistemic probabilities. Classical probabilities are not just always never negative, but they don't come from things that can never be negative the way that quantum probabilities do. So this is really a fundamentally new notion. Well, it gets even more interesting. Suppose we've got two qubits now. The combined wave function could be any blend of the following wave functions: up, 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 down, down, up, down, down. Sounds like I'm doing a Konami code. Okay. Suppose the wave function happens to be a superposition of up, down, and down, up, such as this one. This is now a blend of up, down, and down, up with 50-50 mixing ratios. Well, then neither qubit has its own wave function. Only the composite combined system has a wave function. Erwin Schrodinger called this entanglement in 1935. But notice that if someone measures the first qubit and finds, say, up, then the whole wave function collapses to the up-down wave function. So that means the second qubit suddenly has a definite value. That definite value is down, which it didn't seem to have had before. And this happens no matter how far apart the two qubits are. Einstein called this phenomenon spooky action at a distance. John Bell proved in 1964 that if there are underlying values, we call those hidden variables, behind wave functions, like the qubit really was up the whole time or really down the whole time, something underneath all these weird wave functions, well, then they have to influence each other instantaneously across any length of space, faster than the speed of light. You could imagine why Einstein was unhappy with this. Why, it would be as surprising as two car crashes happening to two entangled people in two different places. at exactly the same time. Note, the no communication theorem, also known as the no signaling theorem, guarantees that this effect cannot be used to send messages faster than light. Sending messages, actual messages, like, look out, that's still limited by the speed of light. This is something a little more nuanced, a little more subtle. And it's a good thing, too, because through a quirk in Einstein's theory of relativity, being able to send messages faster than light wouldn't merely be aesthetically unpleasant for Einstein, but could be manipulated to send messages backward in time. I wish this echoed at that moment. That would be perfect. Okay. Why, it would be as bizarre as getting a confusing phone call about a 1970 musical album like Santana Abraxas in 1967. Like Einstein, Schrodinger was also displeased with the state of quantum mechanics. In 1935, it was a busy year for him, he wrote the following. One can even set up quite ridiculous cases. A cat is penned up in a steel chamber, along with the following diabolical device, which must be secured against direct interference by the cat. In a Geiger counter, so Geiger counter is a device for detecting radiation. In a Geiger counter, there is a tiny bit of radioactive substance, so small that perhaps in the course of 1 hour, one of the atoms decays, but also with equal probability, perhaps none. If it happens, one of those atoms decays, the counter tube discharges and through a relay releases a hammer, which shatters a small flask of hydrocyanic acid. If one has left this entire system to itself for an hour, one would say that the cat still lives if meanwhile no atom has decayed. The first atomic decay would have poisoned it. So the wave function of the entire system would express this by having in it the living and the dead cat, pardon the expression, mixed or smeared out in equal parts in quantum superposition. Lowry was nice enough to provide a convenient visualization. A live cat, dead cat. Flask not broken, flask broken. Schrodinger's cat has become the Dybbuk of physics, neither alive nor dead. In theory, it's only if one is bold enough to measure the cat's state that the collapse will collapse to one possibility or the other. That is if you do the experiment under super precise conditions. Realistically, it's very hard to isolate a cat so perfectly, especially any of the cats I've met. I want to say a little something about the Metaculus. The name will make sense once you see the movie. So in an interview, Michael Stolberg, he plays Larry, he explains, the Metaculus is actually taken from a friend of the Coens who wrote this thing called the Metaculus. It was the same thing, someone who was trying to create a probability map of the universe and probably went a little mad in the process. There's the Metaculus. And this is an interesting little Easter egg from the book. Also known as the God particle, although physicists hate when it's called that. It's proposed by Peter Higgs in 1964, but actually it wasn't called the Higgs boson until long after 1967. Very interesting. So, and by the way, it's backward because Hebrew letters go backward. That's why it's written backward. Contemporary philosophers of science, David Albert, who's at Columbia, Barry Lower at Rutgers, reappropriated the Metaculus. They reappropriated the word. David Albert, in his book After Physics, writes, start then with the initial large-scale description of the universe, coarse-grained, bird's-eye view of the universe. Find the probability distribution over all the possible exact fine-grained descriptions of the universe, a probability distribution that's fair and uniform with respect to the standard statistical mechanical measure, over the subset of those fine-grained descriptions, which is compatible with that initial large-scale description and zero elsewhere. That's a lot. Anyway, the point is, there's some probability distribution assigned to all the different possible ways the universe could have been arranged. Take that probability distribution and evolve it forward in time by using the exact laws of physics, the exact microscopic dynamical equations of motion. The result is a numerical assignment of probability to every formulable proposition about the physical history of the world, and call that latter assignment of probabilities the Metaculus. Okay? So again, if you assign a probability to all objective features of the detailed initial configuration of the universe, and you know the precise laws of physics, then in principle, you can determine the probability of every objective feature of the universe for all of time. That's what they call the Metaculus. So they called it the probability map of the universe. And it serves various purposes in the philosophy of science, the metaphysics of laws. Google it, you'll see a lot of work on it. Okay. In quantum mechanics, there's this construct called the density operator. It's sometimes written as the Greek letter rho, sometimes it's written as a capital W. And so actually there's a whole line of research now called the Wentaculus. Okay, it's interesting. All right, some closing thoughts. As you watch the film, be on the lookout for the following: the appearance of probabilities, uncertainty over whether a thing is X or not X until some action is taken. Is it a bribe? Is it blackmail? Look out for one thing or person that has two seemingly contradictory characteristics at the same time. Note the importance of taking different perspectives. Be aware of any fuzzy boundaries, like backyard divisions. Look out for any interference. Antennas, anybody? And two events connected instantaneously across space. Okay, I also just had to mention the chalkboards. Mathematicians and theoretical physicists love chalkboards. If you walk around our physics department, you'll see chalkboards on all the walls. This movie has a lot of really great chalkboards. Finally, as one character in the film says, embrace the mystery. Thank you and enjoy the film.